also would like to welcome you to this session on inhomogeneous phases. And in fact, I'm very pleased, or I was very pleased to see that this topic was put on the agenda of this great workshop, because even though some people are working in this field already since a decade or so, it's not very often seen in a conference as a dedicated topic. Okay, yeah, and in this session we have 5 talks with 6 speakers, as you will see. And I think we can already start with the first one by Stefano Carignano from Barcelona University, and he will give, I guess, some general introduction also to the topic about crystalline chiral condensates in dense quark matter. So please.
Hi, can you hear me?
Yes, very well.
Okay. So now I'll try to share my screen. I hope that you see it.
Yeah, that works.
Okay. So should I start?
Yes, please.
Okay. So hello everyone. And thanks for the invitation to be here and talk a bit about some recent and also some not so recent work on inhomogeneous chiral condensate in dense quark matter. As Michel said, I will try to give a bit of an overview. So what are we talking about when we say inhomogeneous chiral condensates? How do we study it, especially within, from my side, simplified models, and hopefully present a lot of results. Now, given the audience, I guess I don't need to convince many of you that this is relevant. Studying dense QCD is relevant for astrophysical scenarios, for avion collisions. In general, it's just an interesting question because we have a strongly coupled system at finite density. So, and well, of course, this is the mandatory slide on the QCD phase diagram. And still, after many years of working on this, I still find that people have this picture in mind. So they will think about some low energy confined phase where you have hadrons, where chiral symmetry is spontaneously broken, and then you reach at high temperature and also to some extent density a quark gluon plasma where things is deconfined, chiral symmetry is restored, so quarks are massless again. And then separating these two phases, people still think, most people would think that there is some kind of first order transition ending at some sort of critical point. Then, of course, at very high density, we know we are going to have a color superconductor at some point. But if you really think about it, maybe if you want to be honest, we should remind ourselves that what happens in the middle is, to some extent, a very educated guess. So we're not 100% sure. We don't have lattice simulation, experimental data, both from astrophysics and from avion collision. It's not quite there yet to give us precision things. We cannot do perturbation theory here in the middle. So it is still an open question. And in particular, I would argue that in this space, some spatially modulated condensates might actually form related to the, in my case, to the chiral condensate. So the idea of inhomogeneous spaces in strong interaction matter is not a crazy one that I came up with. Actually, it was already discussed in the 60s or so when talking about P-wave pion condensation. And I also invite you to follow, I think it's tomorrow afternoon, the talk by Massimo Mandarelli about some kind of inhomogeneous pion condensation in a slightly different flavor, let's say. Then, as we will hear in the following, inhomogeneous phases also appear in the lower dimensional toy models, like the Grosvenor models and things like that. So this is also some place with some strongly interacting system where this kind of crystals might occur. Then, of course, many people know about the idea of inhomogeneous color superconductivity, Love phase, stuff like that. And then there is the quarkionic matter hypothesis, which also has its own inhomogeneous phase. There are quarkionic chiral spirals. And then, of course, there are many more. For example, Tomasz, I think at the end of this session, we'll talk about this chiral soliton lattice. So it is not such a wild idea. And in particular, in my talk, as I said, I will talk about inhomogeneous chiral condensates. And I think Efrain on Monday already somehow introduced the idea that I'll just repeat it briefly. So we mostly think of the chiral condensate as some particle, antiparticle condensate, quark, antiquark. And then we say, okay, when we crank up the density of the system or the chemical potential, we start forming a Fermi sea. We have to start digging up antiparticles deep within the Dirac sea. And then at some point you reach some kind of, let's say, critical density. And where this kind of pairing becomes disfavored because you just need too much energy to pull these guys up. And then the chiral condensate melts. and you reach chiral restoration. However, if you form a Fermi surface, you might think of alternative pairing mechanisms. And one of them is the particle-hole pairing. So if you think of a particle and a hole flying with the same momenta and pairing them, they could form a pair which carries a net momentum. And if you Fourier transform this guy back, something which carries a momentum will have a spatial dependence. So there you have your, this is a simple way of thinking about some inhomogeneous chiral condensate, which forms by this pairing on patches at the Fermi surface. Now, how do we study this in practice? We just consider, well, one way of doing this, just to get some qualitative information on this type of feature, just consider a simplified model. So in most of my talk, I would consider the non-Diagonalization model. It's a simple quark model with just a contact interaction. You don't have gluons, you don't have confinement, but still it has some relevant features for low energy QCD. It has chiral symmetry. It supports dynamical chiral symmetry breaking. So this is nice. We expect this, that we expect that it can give us at least some hints on what the physics in this intermediate density non-perturbative sector could be. So we perform the mean field approximation, which again is the simplest thing one can think of. We neglect fluctuations, and we will have talks about fluctuations later on, as a matter of fact. And then you just follow standard procedures, and you can just determine this way the free energy of the system, or the thermodynamic potential, as basically a trace over the inverse quark propagator. So basically, it boils down to diagonalizing some quark Hamiltonian in momentum space. The point is that if you have an homogeneous condensate, well, quark momenta can change, so the Hamiltonian matrix is non-diagonal in an infinite space, or in momentum space. So this diagonalization is kind of tricky. In principle, if you can do it, then you just compute the thermodynamic potential and you minimize it with respect to this mass function, or to the shape of the chiral condensate. And as you can imagine, just doing this with respect to an arbitrary mass function is not an easy task, right? So in order to make the problem, let's say, tractable, what people do, what we did, was to assume a specific ansatz for the spatial dependence of the chiral condensate. And then you can start guessing, right? So you can start with the simplest thing. One can probably think of just one-dimensional plane wave, something which in the context of coarse superconductivity will be a full de Ferrel ansatz. Okay, so this is just a simple ansatz which depends only on two ordered parameters, one amplitude and one wave number. And this is really nice. We like this modulation because we can actually derive an analytical expression for the eigenvalue spectrum without really needing to perform brute force diagonalizations. Okay, so when you try to minimize the thermodynamic potential with respect to these two variational parameters, you find that at vanishing temperature, there is a region. I will turn on temperature later, so don't worry. There's a region of the phase diagram. There's a region of chemical potential at intermediate chemical potential where the system likes to develop a non-vanishing value of Q, so a non-vanishing modulation. And actually, a special feature of the chiral density wave is that even though the chiral condensate is spatially modulated, the density of the system, the baryonic density corresponding to it, is actually spatially constant. This will play a role later on. Now you can come up with more complicated modulation. You can add up two plane waves and you form a cosine. So this would be what in the context of coarse superconductivity would be a Loff phase. And now you already start to have, you already need to do numerical diagonalization. And this becomes numerically intensive and all that, but still doable. And you find similar behavior for the ordered parameter. So again, this kind of modulation is favored over the corresponding homogeneous broken and restored solution in the finite window of the phase diagram. Then another more, let's say, refined solution would be what people refer to as a real kink crystal. And this is just an ansatz which is expressed in terms of Jacobi elliptic function. And you see these are three possible shapes that this kind of function can assume. And you see this is a very general function. It can go from an hyperbolic tangent to a solitonic shape to what basically is just degenerate with a sine or a cosine. And then you can make your life harder by considering higher dimensional modulations. You can build up different lattice structure and you just plug this into your Hamiltonian, diagonalize it numerically in momentum space, you see what comes out. And you always see that all these kind of phases are favored basically always in the same ballpark, in the same region of the phase diagram. So the natural thing to do is just to compare the free energy of all these phases and see which is the favored one among all the ones we consider. And this is the result for the one-dimensional modulations we consider. So you see that the real king crystal solution expressed in terms of Jacobi elliptic function turns out to be the one with the lowest free energy, so the most favored one. Okay, the cosine goes very close, and the chiral density wave, so just the plane wave, is disfavored compared to it. If you include two-dimensional modulations, you see that the one-dimensional Jacobi elliptic function, so the real king crystal, still wins over the square and the hexagon lattice. Okay, and this is as far as we went, because this was already very computationally intensive, but still it seems that the most favored solution is just this one-dimensional, of all the ones we consider so far, is this one-dimensional real king crystal. And now if we turn on the temperature, we can cook up a phase diagram. So for homogeneous phases only, if you just allow for homogeneous phases, this is the phase diagram that people usually get in the NGL model. Just the first order phase transition separating an homogeneous broken and the restored phase ending at the critical point. But if we now allow for inhomogeneous phases, we find that there's a whole window in the phase diagram where these inhomogeneous phases end up being favored over the broken and the restored solutions. And actually this right phase transition to the restored phase turns out to be always second order and basically amounts to the amplitude of the modulated condensate melting gradually to zero. And the order of this phase transition on the other side, on the other hand, depends on the shape of the modulation considered. It could be first or second order, but this is a detail, I will not go to it. And what is also interesting is that now there's a tip of this inhomogeneous phase where the homogeneous broken to inhomogeneous to restored, and the usual second order line if you consider the chiral limit meet. So you have three phase transition meeting at this new special point, which we now call a Lifshitz point. So which is the point where these three phase transition meet. And actually we will see that this actually coincides with the position of the critical point for homogeneous matter, at least in the simplest model iteration we consider so far. Okay, all this was nice, but this was, as I said, you just had to put in some specific ansatz for the spatial dependence of the chiral condensate, and so this one could say, okay, how general is this? So we can try to think of some modulation, if you wish, independent way of attacking the problem, and this is to perform a Ginzburg-Landau analysis. So you just expand, the idea is you just expand the free energy close to this critical Lifshitz point where the amplitudes and the gradients of the order parameter are small. So you just build up an expansion where you consider all the possible terms. And if we look at it a bit closer, you see that, okay, you expand on top of the restore phase. So this is just some restore contribution, which we don't care much about. And then you start ending up all the pieces without gradients. So all the possible powers, m squared, so condensate squared, condensate to the fourth, condensate to the sixth. Now I did this for a real modulation. If you want a compass modulation like a plane wave, you would have to start putting modulus squared when required, just to make things more readable, I guess. And then you start adding all the possible gradient terms, which are allowed by symmetries, rotational symmetries, chiral symmetry, and all this. So in principle, it is straightforward. And actually, the Ginzburg-Landau coefficients themselves, which contain the T and mu dependence, are relatively easy to compute. What is tricky, however, is to compute the relative prefactors between all the possible terms which appear at each order. And to the best of my knowledge, there is no best way of doing it than just taking the quark propagator and performing gradual expansions, collecting terms, and this becomes very tedious already at order 6. If you go to order 8, it's a bit of a nightmare, to be honest. But still, this kind of pays off because we already get a non-trivial result at lowest order. Namely, we find that actually the same Ginzburg-Landau coefficient multiplies the m to the fourth term, which is the one that would allow us to determine the location of the critical point when restricting to homogeneous matter only. But the same coefficient is also the one that multiplies the first non-vanishing gradient terms, which is the one that will allow us to find the location where there's an instability towards the formation of an inhomogeneous phase, so of the Lifshitz point. And this in turn tells us immediately that the critical point and the Lifshitz point coincide, independent on the modulation of the order parameter considered. Okay, so the Ginzburg-Landau approximation is really nice and it's powerful, but of course, strictly speaking, it's valid only close to the critical point at the Lifshitz point, where we know that both the amplitudes and the gradients are small. But some time ago, we sat down and thought, okay, can we do something better? Can we cook some kind of hack to make the Ginzburg-Landau expansion work, let's say, more away from where it's supposed to work? And now, so we sat down and we thought, okay, if you think of the typical behavior of the order parameter for all the modulation we consider, you have some kind of, you come from an homogeneous phase where you don't really care about the gradients. And then we know that the homogeneous phase typically ends in a place where the amplitude is small and the wave vector is large, so it will be a place where you will not need so many values of the other parameter, but rather the piece with the most gradients will be the most relevant one. And of course, in the middle, okay, it is very likely that we will need all these extra pieces that people have cooked. But then we thought, okay, we could actually do something better and resum all these, if you wish, homogeneous pieces into some kind of homogeneous contribution, which is easy to compute analytically. And then actually we could extract all the leading gradient terms by extracting them from the free energy computed for a chiral density wave, which, as I said, we were able to compute analytically. So you can just expand these guys in terms of the Q of the chiral density wave. You collect the terms with the most Qs, order by order. And these are really straightforward to extract. So you can just cook them up to arbitrary order straightforwardly, okay? And then you keep all these intermediate terms in the middle that people have computed already, and you hope that up to order 8 is good enough, okay? So we said, okay, does it even work? So we just try to minimize this Ginzburg-Landau, this improved Ginzburg-Landau potential at t equals 0. So this is the full numerical result for a chiral density wave. And this is what happens if you just try to minimize it at t equals 0, so very far away from where this is supposed to work, up to order alpha 6. And you see that the other parameters do not really come out right, although still you start getting the correct feature at least. Now, if you go to alpha 8, so one order more, well, you start getting closer. And then if you start using our approximation and you go to order 10, so this is already beyond what was computed before, you see that the agreement becomes even better. And already at order 12, you get basically perfect agreement with the full numerical result. Okay, so this is just some nice method. We checked with several modulation. We checked for the free energy and all this. This is just to show you that it's just some nice hack that somehow turned out to work, away from extending the validity, the regime of the Ginzburg-Landau approximation. Anyway, some other methods somehow similar in spirit, if you wish, to the improved Ginzburg-Landau analysis is to perform a stability analysis for the chiral condensate. So you just try to determine basically the right phase transition, so the second order transition from the inhomogeneous to the restored phase. And to do that, you just expand your terminal potential to the quadratic term in the condensate, but you don't perform any gradient expansion. Instead, you keep the momentum dependence in this correlation function in a scalar and pseudo-scalar channel, and you will find the minimum for this correlation function. And if you find that at some point this correlation function changes sign, well, this means in turn that it becomes energetically favored for the system to form an inhomogeneous phase in this given channel. So you can use this method also to determine this inhomogeneous restored phase boundary, to determine whether there is an instability towards the formation of an inhomogeneous phase. Anyway, okay, I think I'm already running a bit late. So this was just a bit on the method, and now I want to discuss some results. So basically, I already showed you some basic phase diagram, and now I would like to discuss what happens if you try to extend the model to give it some more realistic, realistic description of dense matter. Okay, so far we just, as I said, we just computed a very simple model. There are several model extensions you can think about, and there are many I will not discuss, but they are actually interesting. But anyway, we can leave this for discussion. What I want to talk about a bit first was what happens if you include vector interactions in the model. Now, this is a popular extension when dealing with when studying dense matter. You just introduce a repulsive interaction in this vector channel, and if you do the mean field approximation, you see that this basically boils down to a shift of the chemical potential, which is proportional to the density of the system. Now, as I said, the density of the system can become in principle modulated, except for the chiral density wave, which is a special modulation in a way. So in principle, you would have to do things self-consistently and introduce a spatially dependent shift to the chemical potential. And this is kind of challenging to implement. So as a first approximation, we just said, okay, what happens if you just work with a constant density? We just compute the density, an average of the density, and we just consider an homogeneous shift to the chemical potential. This will be an approximation for most of the modulations considered. It will not be an approximation for the chiral density wave. And what comes out in this approximation is actually that including vector interaction dramatically enlarges the inhomogeneous window in the phase diagram. So you see, you go from no vector coupling, and then you start increasing it. And in the homogeneous phase, becomes larger. And actually, we know that for homogeneous phases, the critical point goes down in temperature when you turn on this vector coupling. But this is not the case for the Lifshitz point, which stays at the same temperature. This could also show with the Ginsburg-Landau analysis already some time ago. So effectively, the critical point and the Lifshitz point split, and you're just left with a Lifshitz point in the phase diagram. So you just no critical point anymore, just an inhomogeneous phase. Okay. Now, of course, this average density approximation is a rather crude one. So we went back to the problem recently, and we thought, okay, this kind of vector interaction actually is a repulsive interaction. So it could very well be that it disfavors inhomogeneous configuration where the density is somehow very unevenly distributed. So it might well favor a chiral density wave modulation where the density is just spread out constant. Okay, so these are just two examples of some possible density shapes for the real King crystal and versus a constant for the chiral density wave. So we just checked, and we found with the Ginsburg-Landau analysis that indeed, at least close to the Lifshitz point, there is a phase when you turn on the vector coupling where the chiral density wave starts becoming favored again over the real King crystal. So inverting this thing that we found back in the day. And this was even confirmed numerically at t = 0 by Marco Schramm, a Michael student. And he found that actually beyond some critical value of the vector coupling, the chiral density wave becomes favored over a real modulation, you consider a cosine for simplicity, but still we expect this to be the same for the vector coupling, for the real King crystal. Now, another thing we considered was going away from the chiral limit. All these results I showed you so far were away from the chiral limit. And then when you go away from the chiral limit, you start getting issues of cell consistency with some ansatz with some solution for the chiral condensates, like the chiral density wave. So again, we just worked out a Ginsburg-Landau approach, which doesn't really care about the specific shape of the modulation. You start getting additional terms in your Ginsburg-Landau expansion because chiral symmetry is now explicitly broken at the level of the Lagrangian. And we sat down and we found that basically the critical point now location is given by the point where this cubic term would be 0, whereas the Lifshitz point is still the point where the first gradient term will be 0. So in principle, these points could now split because these are two different coefficients, but actually we sat down and computed them. We found that they're actually proportional to each other. So the critical and the Lifshitz points will still coincide even away from the chiral limit. Another extension we consider, I'm going quickly now, is what happens if you consider 3-flavor quark matter. Again, you include this flavor mixing determinant, you have an additional coupling, you can play with a strange quark mass. And again, we cooked up some Ginsburg-Landau expansion, and we found that for a parameter set fitted to vacuum phenomenology, the Lifshitz point sits slightly above the critical point. So the critical point and the Lifshitz point split again, although very, very, very slightly for this, if you use a reasonable parameter set. Now, of course, you can play with the parameter, and as a matter of fact, what we did was to try and vary the current strange quark mass in the Lagrangian. And the idea behind this was that we knew that if you turn MS, the current strange quark mass to 0, the first order phase transition for homogeneous phases moves towards the temperature axis. So we thought, okay, maybe if the Lifshitz point follows closely, we could try to drag the inhomogeneous phases all the way to the temperature axis and maybe find some, totally unrealistic playground scenario where we could get an inhomogeneous phase all the way to 0 chemical potential, okay? Something which even some lattice study, some weird lattice study could think of attacking in the future. But unfortunately, this turned not to be the case. So the critical point moves, of course, to the temperature axis, but the Lifshitz point does not follow. This location is not even reliable because you have a critical point above the Lifshitz point. This is a technicality, but this is just to say that this is not the case. We do not expect an inhomogeneous space to go all the way to the temperature axis, even when playing with the parameters. Now, there's a lot more things I didn't talk about. And of course, I think it would be very interesting to discuss about some consequences for compact star phenomenology or even heavy-ion collision, but I really don't have time to talk about this. And of course, there's the big elephant in the room, fluctuations. And Martin will give a talk about this later. So, right after me. So I encourage you to follow it. Just as a warm-up for his talk, I will just briefly discuss some mean field or extended mean field results we cooked up when studying inhomogeneous phases in the quark meson model. Okay, so quark meson model, another simplified low energy model. In the mean field approximation, it's really very similar formally to the NJL model, but it has this great advantage of being renormalizable, and it is a better starting point to study the role of fluctuations. But funnily enough, until relatively recently, people were not even considering the role of quark vacuum fluctuations in the model. They were just considering quark thermal fluctuation. As a consequence, they were getting some unrealistic phase structure. Already for homogeneous phase, you will get a first order transition anywhere. And for inhomogeneous phases, here, yes, you will get an homogeneous phase going all the way to the temperature axis, which is clearly not realistic. So what we did was we sat down and we tried to include vacuum quark fluctuations into the model, okay? And then we realized that things are always more complicated than they look. We had to sit down and think about how to fit the parameters in the model, but I think Martin will we'll talk about this later. So just I will just skip this just to tell you things that are not as trivial as they look. But anyway, if you try include properly what we believe is the proper way of including fluctuation, the quark fluctuation, vacuum quark fluctuation do shrink the inhomogeneous phase back to, let's say, a more reasonable size. And even in the renormalized limit, you still get a tiny but finite inhomogeneous window. Okay, and actually we found that the critical point still coincides with the Lifshitz point if the sigma meson mass we choose is twice the vacuum quark mass, which is actually the Nambu-Lasinho relation, which comes up naturally in the Nambu-Lasinho model. Actually, we even sat down and played around with the influence of the sigma mass. If you just pick a larger sigma mass, the critical point, the Lifshitz point actually moves up and you get a larger inhomogeneous phase, and the critical point, the Lifshitz point split, but I will not talk much about this. Just one final word. What happens if you go in the renormalized limit of the quark meson model away from the chiral limit? And this question was kind of came to us because some other clever people found that the chiral density wave actually seems to disappear from the phase diagram if you go in the renormalized limit for a physical pion mass. But then we thought, okay, actually the chiral density wave is kind of a special modulation where the pseudoscalar part and the scalar part are closely tied together by the same amplitude. Okay. So we just tried a stability analysis, and we just checked what happens at the stability in the scalar and pseudoscalar channel. And we found that when you go away from the chiral limit, actually these two stability lines split, and the instability line in the pseudoscalar channel disappears quickly when you crank up the pion mass, which is the numbers given here. On the other hand, the instability in the scalar channel also goes down somehow, but is still there for a physical pion mass. So we expected for a real condensate, for a condensate where, yeah, just for a real condensate like the real king crystal, this kind of inhomogeneous phase will still be there away from the chiral limit in the renormalized limit. And we actually checked this numerically with the real king crystal ansatz generalized away from the chiral limit, and we found that there is still an inhomogeneous window surviving. Okay, now this is the usual disclaimer I put at the end. One can argue, okay, maybe this is just a model artifact, but other people have found them in Dyson-Schwinger studies and even functional renormalization group studies, but I should not be the one talking about this. This brings me to my conclusions. So I always end up with this slide. People should maybe stop thinking about this kind of phase diagram and maybe think of it more in this term. So this is my version of the phase diagram, and I think I already talked enough, and I thank you for your attention.
Yeah, thank you very much, Stefano. The time is almost up, but yeah, first of all, thank you for even setting the stage for the next talks. We will have a discussion session later, but still, I think there would be time for 2 or 3 questions, I guess. So if you want, please. Yeah, okay, I see one hand raised. The first one is, I'm not sure about the pronunciation, Lucha Machaldiani.
Yes.
Yeah, okay.
It's family name. We see that in such an environment inside of hadrons, for example, we have some non-trivial geometry, some lattice picture. So we can simulate in this background as a real lattice simulation, not just as in lattice gauge theory as artificial tool lattice, but really we have lattice. And we can simulate as if we simulate solid state, some crystal like picture or model. It's my comment. Thank you.
Okay.
So I see another hand raised by Mark Wagner, who, however, has a later talk anyway. But Mark, is this directly?
Yeah, I wanted to ask about the NGL results. As you said, the NGL model is not renormalizable, so you have a cutoff and maybe one or more possible regularization schemes. Do you observe or know about the dependence on this regulator?
Okay, regularization of inhomogeneous phase in the engine model deserves a 1-hour talk by itself. The idea is that you should definitely not use sharp momentum cutoffs, because this would, when you think about this is just a bad idea when your quark momenta is not really conserved anymore. So this would just spoil everything immediately. So we just use, in most of this work, we just use some Pauli-Villard regularization, which is nicer and just behaves nicely. And we even check, you can even do things in the proper time regularization. This we also checked. So the inhomogeneous phase is still there.
And when you say the momentum cutoff spoils it, is there a physics reason why you shouldn't use it, or is it just gone and you say it's less interesting then?
No, I mean, okay. So it's just that if quarks scatter with the condensate, which is of the order of the chemical potential, which has a momentum of the order of the chemical potential, which is always dangerously close to the cutoff, you're just artificially reducing this space for your quark to form an inhomogeneous condensate.
I think this cutoff business is something we could really take up again in the discussion session, because also, of course, in your talk, Mark, it will play a role.
Sure, this is why I'm asking.
So we should wait for that, I guess.
Thanks, Stefano.
Last question by Maxim Janudin.
Thank you. Thank you very much, Stefano, for a nice talk. I would like actually to give a quite provocative question, maybe even the comment. But, you know, usually we look for ground state in such models like Nambu and Lazinho. We look for Hermitian ground states. So we have condensates which are Hermitian. But there is a wide class of models which can admit non-Hermitian ground states which are still stable. So they have all eigenvalues of all excitations quasi-particles that are have non-instability. So they have positive or real valued masses and energies. So, and those states, inhomogeneous, those states which are non-Hermitian, they may also admit Ginsburg analysis in similar way as you discussed. They may admit inhomogeneities, but in non-Hermitian sense. So I would like to say that it's a perfectly stable ground states which are non-Hermitian. So do you have any comment on that?
Sounds interesting, but I have no idea.
Okay, so just maybe we can talk later. Or
yeah.
That there is some extension which perfectly agrees with the common sense in the sense of stability, but disagree in the common sense of hermeticity, which it does not prevent the system to be there.
I guess there are always possibilities nobody has thought of, and which could be even better ground states. Yeah, thank you for this comment, and thank you again, Stefano.